Hi everyone. Today today's presentation is about atmospheric energy and global temperatures, two very important concepts in both weather and climate. Right. And just before I start today's lecture, I'd like to remind you again that I didn't post. There were no lecture videos were posted on Monday because I was receiving emails from students. We didn't expect that we were having classes, and those were for my in-person classes, and would like to make sure that both classes are going at the same speed. So for this week, we will only cover the atmospheric energy today's lecture, and then the attendance quizzes for the week will also focus on the atmospheric energy and global temperatures, right? So there are very key elements of today's presentation, but most importantly, we'll start by reviewing the Earth's energy budget, right? We'll come to this point again and again throughout this lecture. But in doing so, I will also go through very important concepts in heat transfer mechanisms, the concept of temperature, and then global temperatures, and then how it has been changing and how humans have been affecting it, right? So when we talk about the Earth's energy budget, there are about four important processes. And these are the transmission, absorption, scattering, and reflection, right? And I'll say this again, without the atmosphere, we can't actually sustain, we won't be able to sustain life on this planet, right? Because our existence in this planet is both directly and indirectly impacted by the sun, right? So for instance, the atmospheric window, the atmosphere through what we call the atmospheric window allows the parts of the solar radiation that's useful to sustaining life on Earth, right? So there is this transmission which refers to the passage of shortwave and long-wave energy through the atmosphere or water, right? But what the atmosphere does is it actually prevents us from what we call those harmful shortwave radiation, and it allows the relatively longer long-wave radiations, right? So it absorbs or scatters or reflects those harmful radiations as best as it can, right? And then we talked about, for instance, the ozone layer, the destruction of the ozone layer, why it is very important, right? So, for instance, the purpose of the ozone molecules in the stratosphere, as you'll see, as I will remind you again in the next slides, is to prevent us for one of the harmful shortwave radiations in the form of UV radiation, right? So when we talk about the energy balance, of course, part of the solar radiation coming to the Earth is transmitted to the Earth or also absorbed, and part of it is scattered back to space. So the difference between scattering and reflection, very similar terms, but reflection, we're actually now talking about the radiation, the incoming solar radiation, bouncing back at an angle, right? So scattering is more random. Practically, that's the only difference, right? So when we look at the Earth's atmosphere energy budget, right? So what we see is, well, we have the sun, right? That's the ultimate source of energy to this planet. And then we have the clouds and different particles in the atmosphere, right? This needs to be corrected. I'm sorry about that. Yeah. Okay. So the sun, there are different particles that we have in the atmosphere, right? So there is the first interaction between the incoming solar radiation coming from the sun, as you see here in the picture, is actually what's present with the atmosphere, right? So there is obvious scattering and reflection going on because we also have those thin clouds, different types of clouds that we covered last lecture. And then, most importantly, but what I want you to focus here is there is also emission from the surface, right? So whatever the amount of solar radiation reaching the surface, that's part of it is also absorbed by the surface, the Earth's surface, right? And then if a body absorbs a heat, it doesn't matter whatever type of energy, there is also that means if it absorbs the radiation, then there is it's also a source for the radiation that's supposed to go out, right? So we'll always have this long wave radiation. Typically, if we didn't really have the greenhouse effect, that would escape to the space and then helps us to maintain the energy balance, right? That energy equilibrium. But what happens is because of the greenhouse effect, right? Because we're also emitting this very powerful greenhouse gases like carbon dioxide, methane. So what happens is that these greenhouse gases are very, very potent at absorbing that long wave radiation that would otherwise escape in normal circumstances, escape to space, and they help us maintain that energy balance. But what happens is that while those greenhouse gases are trapping the heat, right? So what we call the greenhouse effect is those gas molecules absorbing the outgoing long wave radiation and sending that heat back to the surface again. That's actually what's causing global warming, right? So what we call the greenhouse gases effect is that those gases are serving as a blanket, right, in the atmosphere, thickening the blanket, right? So with more, as we continue to thicken that blanket, that atmospheric blanket, then there is no way, it becomes harder and harder for that long wave radiation to escape to the space. And what happens is that then we are off balance in terms of the Earth's energy budget, because what comes to the surface is no more living to the space, right? So for instance, typically we have about 314 watt per meter squares of insolation come to the surface, and typically, of course, this should be balanced, right? So some of it is absorbed, some of it is reflected or scattered, and some of it makes its way to the surface. But we always typically, on the ideal scenario, we would meet this equilibrium, right? So what's going out is balanced by what's coming in, right? But what the greenhouse gases do is actually now we don't really have about 239 watt per meter square leaving to space, escaping to space, right? That's much lower because part of it is being absorbed in the troposphere, because we have now what we call the greenhouse effect, because of the greenhouse gases like carbon dioxide we are emitting to the atmosphere, and then that sends back the radiation back to the Earth, right? So as we keep thickening this, this portion, right, as we keep emitting these greenhouse gases, what would happen is that, of course, the Earth's energy budget would continue to grow off balance, right? We wouldn't really attain that balance, right? What about during the daily radiation patterns? Remember, so there's one example. So the warmest, if you just like if you think of it, the warmest time, the warmest hour during the day is about 3 p.m. or 2 p.m., right? Around this time. Why is that? Because even if the sun is typically overhead around noon, right? And the warmest day there is a time lag, right? For it to completely the Earth's surface, for it to completely warm, right? But only while around 2 p.m., 3 p.m., even if we still have the sun. The sun is it's not overhead, but it's still not, we're not still far away from noon, right? But what happens is that during this time, it's actually the surface, which has been absorbing that heat that's coming from the sun, starts releasing, it starts releasing that outgoing radiation, right? To to the atmosphere, right, and to the surrounding air. So we have the Earth being added as a source as well, right? So typically around 2 p.m. is the warmest hours of the day anywhere in the hemispheres, right? But if we compare for instance, well, of course, when we talk about the daily radiation patterns, of course, it's also dependent on the type of materials we have, right? So, for instance, in Atlanta, in the summer, typically around 3 p.m., it's like 3 p.m. It's like the hottest time of the day. But it also depends on what type of materials we have, right, for the surface. So, if we have, for instance, asphalt, it's very, very efficient at absorbing that insulation coming from the sun. But like, for instance, of course, if we have trees, it would be different, right? It would be different. So the amount of insulation that is being reflected, right, or reaching the Earth's surface is different, all depending on what covers we have, right? Now we're talking about the surface. So, for instance, look at the Sahara Desert. Like, it's actually about 260 watt per meter square, right? So this is high because there's nothing preventing it from reaching the Earth's surface, right? So there are very important interrelated terms that I want to introduce today. So one of them is heat. So when we call heat, well, we're of course thinking about transfers of energy, right? So for instance, when you think of heat, if your hand is warmer and then one of your hands is colder, so you'd feel the heat transfer, right, from the hotter body to the colder body. Here, in this case, our hands, right, from my right hand to my left hand, right? So heat is fundamentally the transfer of energy from the higher temperature of an object to a lower temperature of an object. So it's in a way dependent on temperature. But there are 4 key heat transfer mechanisms that I would like you to remember, right? So one of them is radiation. That is, so for instance, when we're heating up a pan which has water in it, so there are 4 different processes. Well, I would say 3 different processes, heat transfer mechanisms, like occurring at the same time, right? One is when you're holding the pan, like you'd feel the heat, right? That's conduction, right? Conduction is the molecule to molecule transfer of heat, right? But like it requires a direct contact, right? So conduction is a solid phase to solid phase transfer of heat, right? So here, for instance, you wouldn't see, there is no phase change, right? So it's just a solid phase transfer of heat. And there is what we call radiation. Radiation is, well, even if there is no direct contact, you'd feel that the surrounding air is actually significantly warmer, because that represents the heat energy traveling through air or space, right? And then convection is what we have inside the pan, where we have the water molecules transporting energy, right? Warmer molecules that are closer to the pan, as you can see here, moving up, and then transferring the energy vertically, right? And then, most importantly, what we have in terms of when we're thinking about weather and why it rains some places, why it doesn't, we have what we call advection, which represents the horizontal transfer of energy, as I'll explain in the next slide. But advection is also dependent on what we call latent heat and sensible heat, right? Because especially when we're thinking of the weather, why it rains, what's so rainy during the summer season, why we have thunderstorms during the summer season or not during the winter season, is because of these two terms, right? One is latent heat, that is the energy absorbed or released as water changes state, right? So latent heat, that's, as you can imagine, it takes place over the ocean, right? And then we have the sensible heat. That it hits the body, but there is no change in phase. So what happens is that these two work in tandem to create that pressure gradient, right, needed for the advection of energy from the water body through the wind. Because without those pressure gradient, without the differences in pressure gradient, and we can't really have wind, because wind is fundamentally driven by the pressure gradient. So in this case, for instance, this pressure gradient, in this case, what we have is, well, we have evaporation taking place, right? Latent heat, and then of course there is more moisture, that means released to the atmosphere, and that is the energy and the water vapor being transported to the land surfaces, right? That's typically how we have the starting point of what we call this strong monsoon formations. These are about the monsoon. I believe that we have a lecture, or we may have already covered it, but like we'll talk about the monsoons in the next lectures. But of course, at any given point, we also have this constant interactions, like I said, between the spheres, right? But we also have, like, if we're, for instance, near a water body, we have the convection and then latent heat and sensible heat over land. So typically over the ocean, what happens is, of course, as we have evaporation, there is a phase change from liquid to the water vapor, to its gaseous form, right? So if you look at the global latent heat of evaporation, of course, it will be higher near the tropics, right? So there is that where we have abundant water, right? So near the tropics, latent heat of evaporation would always be higher, right? So that's where typically throughout the season, where the sun is nearly overhead, and then where we have abundant insolation, the amount of insolation that the tropics receive is considerably higher compared to the poles. So the latent heat of evaporation will always be higher over the ocean compared to land. But even if you look at the land, for instance, there are significant differences. For instance, here we have the Sahara Desert, where it is like among the lowest, and then we also have the tropical forest, while it's relatively higher, because we have abundant moisture also available in the tropics, right? Okay, so heat and temperature are very similar, but when we're talking about temperature and the scientifically how we define it is, it's a measure of the average kinetic energy of individual molecules in a matter, right? The higher the kinetic energy, the higher the temperature, right? So, but heat and temperature are related because changes in temperature are caused by the absorption or emission of heat energy, right? When a body absorbs heat energy, it also increases the kinetic energy, right? And then it also becomes like whatever body absorbs heat, it also automatically turns into a source, right? So temperature and heat are very, very similar and can be used interchangeably, right? But there are very important controls on temperature, right? And we know that, for instance, latitude is important because the location where you live actually controls the amount of solar radiation that places receive, right? So if you live in the tropics, of course, the temperature will always be higher compared to if you live in the poles. But altitude and elevation, cloud cover, land water heating differences are also important. But what I want you to remember is, even if latitude is important, for instance, these three parameters can also make up or compensate for the differences that a change in latitude causes in temperature, right? So, for instance, if we look at the Earth's energy budget by latitude, of course, the poles will always be colder than compared to the tropics, right? So there is surplus energy that's accumulated in the tropics, right? Throughout the year. Well, of course, the warmest temperatures, of course, slightly shift northward and southward depending on the seasons, right? But when plus or minus 2 degree north or 2 degrees south, so there is that difference, right? The what we call the intertropical convergence zones, it moves northward and it also moves southward, right? So low latitude, if you reside in low latitude areas, so for instance, our best example here in the U.S. is Hawaii, right? Or we can say Florida as well. So, of course, it's Miami. And if you check the temperatures today in Miami, probably it's about 80 degree Fahrenheit, right? So those low latitude regions, they tend to have high average temperatures throughout the year, right? And low temperature range throughout the year. What do I mean by low temperature range? Well, the difference between their coldest seasons and their warmest season is actually not that big, right? I'll give you one example. For example, think of it, Atlanta, right? The highest temperature, like typically in July or August, the highest temperature, land temperature here in Atlanta, is about, let's say, about 95 degree Fahrenheit, right? And then in the winter, sometimes we can have, like, on average, winter temperatures in Atlanta are about 50 degree Fahrenheit, right? So there is about 40 degree Fahrenheit difference between the coldest season and the warmest season, right? So, but if you go to, for instance, Miami in Florida, you can check it yourself. Well, temperatures during the summer are all about maybe about 100 degree Fahrenheit, 105 degree Fahrenheit, right? But even if it is so humid, well, temperatures are about 100 degree Fahrenheit, right? That's the highest range. But during the winter, even during the coldest seasons, temperatures don't go below 70 degree Fahrenheit, right? That's the tropics. So the gradient in temperature between the lowest temperature and the highest temperature is close to 30 degree Fahrenheit, while that's double the amount in places like Atlanta, and then it gets even higher as we move closer to the poles, right? So for instance, if you look at Montreal in Canada, Quebec, well, the warmest temperature is about in July about 70 degree Fahrenheit, right? While the coldest temperature is typically recorded in January, that is about minus 10 degree Fahrenheit, right? You see the difference? There is 80 degree Fahrenheit difference. While, so for instance, if you look at Brazil, not very far away, it's about 13 degrees south. Well, not really far away from the tropics compared to Montreal, but the difference is about like it goes from 50 degrees. It's very similar to Atlanta. It goes from 50 degrees to 80 degree Fahrenheit. That's about 30 degree Fahrenheit differences, right? So latitude is a very important temperature control, but altitude is also very important. Why? Because we know that like temperature significantly decreases as we go up, as we climb a mountain, right? Temperature significantly decreases, right? Up to a certain point. Well, the stratosphere, of course, that's way up, right? That's we're talking about like 18 kilometers above the surface, right? So we don't really have those mountains like as big as reaching the troposphere. But what we have is typically the entire topography of the Earth is within the troposphere, right? Within this range. So the temperature actually decreases with height. So there is actually, it's possible altitude can compensate for the latitude, the latitude impact. So I would like you to check today's temperature in Indianapolis and Reno, right? So different places, different altitude, but they reside on the same latitude. But the temperatures today are significantly different. Why? Because the altitude is very different. The topography is different. So topography can actually, in many cases, if you reside in and in mountainous regions, even if you're not very far away from the tropics, and technically the place receives abundant, there is surplus insolation being received, but the altitude can compensate for that temperature surplus, so it doesn't feel that it is warm enough, right? So, and cloud cover. This is also very important because as I show you in the first slides, so for the energy budget, the clouds are very important, right? So when we're talking about solar radiation, part of the energy is being absorbed, and part of the energy is either transmitted, part of the energy is scattered or reflected, right? So as long as we have clouds, there is that constant interaction, right? So for instance, the clouds, they may reflect those harmful radiations, right? But when we're talking about when we're talking about, for instance, the long wave radiation, that is different because the clouds are actually, in terms of looking at the short wave radiation, they are actually very good at reflecting or scattering the incoming solar radiation. But for the longer wave radiations, they are actually very efficient absorbers, right? They can absorb the long wave radiation that is being released by the Earth's surface, right? So what happens is that, well, clouds end up having both a warming and a cooling effect. Why do they have a cooling effect? Well, of course, there's a cloud that they also reflect the incoming radiation coming from the surface, but also they have a warming effect because they have the capacity to absorb the long wave radiation. Okay, I'll explain. I'll give you one example, right? So one of the examples is that, well, if you have clear skies, right? Clear skies at night, it typically in the winter, usually feels very cold, right? Especially weather temperatures, for instance, desert temperatures. Well, the closest we have here is like if you travel to places like Arizona, right, Tucson. So it's during night, if you have clear skies, it's actually can feel really cold, right? Because there is nothing in the atmosphere preventing the escape of the long wave radiation that's being emitted from the surface. While cloudy days, they tend to be warmer. Remember, so clouds, they can have both warming and cooling effect. So, coming back to advection again, I'll just, before I show you one important figure, I just want to touch upon this, what we call the higher specific heat of the ocean and specific heat capacity. It's not actually higher specific heat, it's heat capacity. The specific, what we call heat capacity. So the heat capacity of the ocean, the water, is different from a solid body, right? So for instance, what this means is the amount of energy that's required to raise the temperature of a substance per unit of mass is significantly higher for water compared to solid. So what this means is it takes longer for the water to warm up compared to the land. So what happens? So when we have different heat capacity of the land and the ocean, what happens is that, well, if we're in summer season, the land always warms up faster than the surrounding ocean. I'll come to this point in the next slide, right? So then again, if we look at, for instance, it doesn't matter the seasons, the global annual temperature ranges are significantly always will be higher in the poles compared to the tropics, right? We don't really have the range, right? And then if you this is the Vostok station, and the Vostok station is where we have the first drill course from the Antarctica, where because of this course we're able to quantify carbon dioxide changes going back hundreds of thousands of years. But in Antarctica, what you see here is there's practically the range in temperature changes, right? can go to minus 24 to minus 66 degree Fahrenheit. So it's really, really the coldest desert, right? It's practically, we don't really have, these temperatures can't really sustain any vegetation types, right? It's too cold. Let me come to this point. So remember, the heat capacity of the water, the ocean is significantly different from the heat capacity of land. So what does it mean, right? So look at this, what's happening in this GIF, right? I'm showing you global temperatures from the 1880s to 2017, right? What do you see here? Like you to take a minute and just try to see what's happening here. So I'll start. So what we see is the global temperatures, like the northern hemisphere is pretty much red, right? The poles in the northern hemisphere is pretty much red, while the southern hemisphere, well, it's warming everywhere. The southern hemisphere is, well, it's warming up. It's not warming as fast. So why do you think is the case? I'll allow you 10 seconds to think about this. So remember, there is a significant difference in the rate of warming between the northern hemisphere and the southern hemisphere, right? Because again, it's because of that, the heat capacity change between the ocean and the land. What do we have in the northern hemisphere? In the northern hemisphere, almost all of the land, right? Most of the land we have at this planet is situated, is present in the northern hemisphere. But like southern hemisphere, it's actually relatively dominated by the ocean, right? So it's always going to take more time to warm the ocean. So that's why you see these differences. So it doesn't mean when we're talking about global temperature, it doesn't mean that like everywhere it's warming at the same rate. But some places are warming much faster than other places because their heat capacity is different, right? If you're looking at the land, of course the land is always going to warm faster than the ocean because it takes more time for the ocean to catch up. So if we look at, for instance, the US, well, what we see here is, well, the West Coast is significantly warmer, right? But like if we look at, for instance, places in Atlanta, the trend is not as strong. So this is very common. So there will always be places that are warming much faster because this is not just a linear response, right? Of course, we're adding the global, but we also, what global warming means is that in some cases, since we are also interfering with the physics, it ends up changing the weather patterns, right? So sometimes, even if global temperatures are, we know as we continue to emit greenhouse gases, we know that the global temperatures are rising, but we still have those coldest days sometimes during the winter, right? While some places are actually getting colder. This is actually because of global warming. Like I'll take you back to this GIF again. Remember, look at here. Well, global temperatures are almost everywhere. It's rising, but I want you to focus here, this area, in northern Atlantic Ocean, right? Here, where the cursor is. We are actually seeing a decrease, right? So it tells you that like we are interfering with the climate system in a complex ways. And then this causes, in some places, some places we see a reflection of this interaction, right? So it's actually because of the global warming and then our interaction with the atmosphere, with the planet, that's causing some places actually to experience the coldest temperatures during the winter. Remember, We talked about the jet stream in the previous lecture. That's the meeting place between the warm air mass coming from the tropics and then the cold air coming from the poles, right? That's the meeting place. So we are actually, by raising temperatures, we are actually interrupting, impacting these atmospheric patterns. And then for some places, for some rare places, rare scenarios, it might mean significant cooling, right? So in some places, the signal we see everywhere else, it is relatively suppressed, right? So that would be it for today. Again, I would like you to go through this GIF again and think of what's happening today. And then, right? And for instance, think of reasons. And one of the questions I'm going to ask you is, why do we see a certain cooling in the attendance quiz? I mean, why do we experience certain cooling in some rare parts of the planet? That would be it for today. And I'll see you with the next lecture video on Monday.